So the last part. So as I was explaining, as in 1D, the slope relates to stress. Like if we assume Young's modulus as 1, the slope is the slope of u versus x plus, the graph, that is du by dx, will be the stress. In 2D, there's some complex derivation from which you can obtain that dou u by dou x and dou u by dou y. The slope in x direction when y equal to constant and y direction when x equal to constant, that is dou u by dou x and dou u by dou y, is proportional to the stress induced in the 2D element in linear interpolation. So in triangle, at any point, the slope would be directly proportional to du by dx and du by dy, and a product between them. Somewhat you can understand. The derivation is complex and you will only understand after covering the entire FEM course. So for now you can assume that this dou u by dou x and dou u by dou y are somewhere related to the slope, to the stress in 2D. So displacement I can say is u is a0 plus a1x plus a2y. So if I take the dou u by dou x and dou u by dou y, what I get are two constants, a1 and a2. So again, from the same analogy what we did in 1D, we can say that the stress along this in this triangle at any point would be constant, and this is natural because using dou u by dou x and dou u by dou y, we can find the normal at any point, and for a single plane the normal will be pointing in the same direction, hence the direction of normal will be constant. Hence basically what I can say is, between these 3 points the value of stress would be constant and won't vary between this point. So if this is 40 MPa at this point, this will be 40 MPa at this point, 40 MPa at this point, anywhere in this triangle. So this is the main problem with triangular element. The stress within the triangular element will remain constant. So if we have such a complex problem and there are stress concentration regions over here, if I expand this, in actual case I should guess contours like this, stress contours like this, from maximum say 100 MPa, 90 MPa, 80 MPa and so on. But if I mesh it with triangles at corner, what I will get is constant stress regions. Like here in this triangle it will be suppose 40, here it will be 50, here it will be 60, and I won't really get the variation that is there and the maximum stress induced at this point, and hence triangular element would give me a bad result because the stress distribution along the triangle would remain the same. The displacement would be linearly interpolated, that is displacement would be linearly interpolated in a plane joining these 3 points 1, 2, 3, but the stress would be constant, and that's the biggest disadvantage of using triangular element. So the one solution of this problem could be refine the mesh, make more fine mesh. So for smaller triangles the stress would remain constant for a smaller region, and you will get somewhat better results than a coarse mesh. Hence this is the basic reason why triangles are not used to capture stress variation in 2D. So like in a triangle, if the stress variation in actual cases like this 10 MPa, 20 MPa, 30 MPa and so on, if you mesh it with a linear triangular element, what you will get is just one value throughout the triangle, that is 40 MPa, and you won't be able to capture the variation in stress, and hence you won't get good results. Now you would say that in softwares when you observe, you can see that there are contours passing through the triangle. So basically that is somewhat called as smoothing. In actual case the software will calculate constant stress along the triangle, and using some graphics algorithm called smoothing, it will just draw the contours so that it will look good to present, you can say. So this is the reason we don't use triangular elements.